Hello, I'm Professor Carla Mercado-Shaker, and in today's lecture, we will discuss about scattering. Now, what is scattering? Scattering is any redirection or disturbance of the incident wave that is propagating in a medium. We talked about reflection last time, and reflection is actually a special case of scattering. And scattering is useful in ultrasound images because it allows us to visualize objects that are in the image. I show an equation of an incident wave in a homogeneous medium which satisfied the wave equation. This you would have seen in a previous lecture. And the total acoustic field that is being generated in this medium is a summation of the incident wave here that's propagating towards an object, and as well as the scattered wave that is being sent back towards the transducer, as well as scattered into different directions, depending on the scattering regime. We also have to consider interactions of those scattered waves that are being emanated from these different objects inside the tissue. So scattered waves from these tissue structures either combine coherently or incoherently. You might have remembered from your previous physics class where you talk about light and optics, where there's two types of scattering, coherent and incoherent scattering. Incoherent scattering, the particles are very close to each other relative to the wavelength scale. So in this case, if the scattered waves that are in phase, they will constructively interfere with one another. And if the scattered waves are out of phase, they will destructively interfere. In terms of incoherent scattering, in this case, the particles are far away from each other relative to the ultrasound wavelength. Here, the scattered energies can be simply added, and constructive and destructive interference does not need to be considered in this case. Now, there is a metric that is used to quantify how much of the backscattered signal is being sent back to the transducer from the tissue, and this metric is called backscatter coefficient. The definition of the backscatter coefficient is the differential scattering cross-section, and that is the power scattered per unit solid angle in the 180-degree direction. When we talk about scattering, the incident wave is actually propagating in the 0-degree direction, whereas the signals that are being scattered back into the transducers from the tissue is in the pi direction, or 180-degree direction. And in this formula, it's also divided by the incident wave intensity. Now we talk about per unit solid angle. So in this case, when we talk about a two-dimensional circle, we looked at the angle in terms of radians. What a solid angle is, it is a three-dimensional angle which looks into the amount of the field of view of that object that's coming from a certain location in space. And the backscatter coefficient can be quantified by this expression, wherein you have the backscattered power in the numerator divided by the solid angle times the incident intensity of the wave, as well as the scattering volume. And this scattering volume just represents the region of interest in your tissue that you are looking at, which you are getting the backscatter signal from. Now, there are three scattering regimes that one can consider based on the size of the object that you are looking at. So it depends on the object size relative to the ultrasound wavelength, and that be quantified by this term Ka, where Ka, as you would have remembered, is the wave number, and that's inversely proportional to the wavelength, and A is the radius of the scatterer. So you can look into this schematic right here, wherein you have a wave field that's propagating, where the dark regions correspond to the compressional part of the wave, and the white regions correspond to the rarefactional part of the wave. And you can see here what one wavelength looks like. And if the particle is of a particular size relative to the wavelength, it defines basically what the scattering regimes are. So there are three that we look at here. If Ka is much, much greater than 1, then we have what's called specular scattering. In this case, typically what happens is there's reflection from smooth planar interfaces. The next regime is the Rayleigh scattering regime, in which case Ka is much, much less than 1. In this case, you get scattering from very small particles in the object, in the medium. And finally, the diffractive or the Mie scattering regime, where Ka is almost proportionally on the order of 1. So in this case, the size of the object is basically approaching the size of the wavelength. Now let's look at each of the regimes more closely. So for specular scattering, what it is the object is much larger than the ultrasound wavelength. So here, our Ka parameter again is much larger than 1. And here we show an ultrasound image of a liver, and typically what you would see in the field of view is also a diaphragm here. As we know, diaphragm is a muscle that helps us breathe. And what you can see is a muscle diaphragm here that appears fairly bright in some cases and slightly darker in a few of the cases. So when we talk about the size of this diaphragm relative to the wavelength, it is fairly large. And here you can see that the object appears good resolution. And typically for a specular scatterer, the detected size is pretty much accurate that you would see in the image. Also, what you would have noticed is that the strength of the signal varies depending on the orientation of the object. So for instance, in this image here, the transducer would be viewing from the top of the image. And as it images through the tissue, you can see that regions that are more flat in this image appear brighter than regions that are more angled. And that is because in specular scattering, the strength of the signal has a strong orientation dependence. If you see the schematic on the right here, you can imagine that the boundary is like a diaphragm. If the incident wave coming from the transducer is going in this particular angle, then the reflected wave will also reflect back at an angle that is equal to the incident wave, but on the other direction. So in this case, not much of the reflected wave is actually coming back to the transducer and being considered as a backscattered signal. So here's just an example of how the orientation of the specular scatterer would be affected and seen in an ultrasound image. Next, we discuss Rayleigh scattering. And this Rayleigh scattering phenomenon was actually derived by Lord Rayleigh, who we have previously discussed before. He had published a book on the theory of sound in the late 1800s. So in this case, the scatterers or the objects are considered much smaller than the ultrasound wavelength. So in this case, in terms of Ka would be much smaller than 1. And what typically happens in Rayleigh scattering here is that you have an incident wave that is going from the transducer. It then interacts with the object and scatters in multiple directions. Now, this scattered signal typically has a weak angular dependence, and typically these objects or the structures in the tissue cannot be visualized. However, such small structures can contribute to the background texture of the image. And what kind of Rayleigh scatterers can be found in an ultrasound image? Well, we know that tissues contain cells, extracellular matrix proteins that are on the order of a micron scale. So when we talk about ultrasound imaging at the clinical imaging frequencies, the wavelengths are on the order of 0.3 to 1 millimeters. And so these cells and extracellular matrix proteins are quite small, much smaller than the ultrasound wavelength. So they are considered Rayleigh scatterers. Now here's just an example of a scattering from a rigid sphere. And this is the mathematical formulation of what a Rayleigh scattering would be, wherein Ka is much less than 1. Although most parts of the body are not so rigid, the rigid sphere approximation fairly holds in terms of the relationship of the intensity and the backscattered wave. So we can see here, we have a fraction of the scattered intensity over the incident intensity, and that is a function of the wave number to the 4th power and the scatterer radius, or the radius of object that we're imaging, and that's up to the 6th power. We also have here the radial distance from the scatterer. So basically, from the transducer to the scatterer, what is that R distance? And theta would be the angle relative to the incident beam. So for backscattered, when we talk about backscattered signal, that theta would be pi, or 180 degrees. So as you can see here, K is to the 4th power. It means that 1 divided by lambda is to the 4th power. So as the wavelength of sound decreases, then the intensity of the backscattering would increase to the 4th power. So one example that we can think of in everyday life is our blue sky. We know that there are gas molecules in the atmosphere. They undergo Rayleigh scattering of light in this case. And we also know that invisible light, blue color, has the shortest wavelength. So this is the wavelength that would scatter the most, hence having the blue color in our sky. So in the body, we have red blood cells, cells that have an approximate diameter of about 7 microns. And if we use 5 megahertz ultrasound with a 300 micron wavelength to view these red blood cells, then you would consider the red blood cells as being Rayleigh scatters because they are much, much smaller in dimension compared to the ultrasound wavelength. Now let's talk about the final scattering regime, which is the diffractive or the May scattering regime. This theory was developed by Gustav May here. And the relationship between the Ka value is on the order of 1, meaning that the size of the object is all the order of 1 wavelength. So you can see here that here's the incident wave and here's a scatterer that undergoes the May scattering regime, where you can see that this scattering has a stronger angular dependence compared to the Rayleigh scattering regime. So when we talk about May scatterers, the object size and its shape in the ultrasound image may not match with the actual dimensions that it has. For instance, if you view a Rayleigh scatter, a point scatter, then the same shape you will see in an ultrasound image. But for May scatterers, this directional dependence of scattering actually impacts what the object will look like in an ultrasound image. So basically, structures in the body that have a size on the order of a wavelength or in the order of millimeters can cause May scattering. So for instance, when we talk about the atmosphere again, we have droplets in the clouds that undergo May scattering of light. So some of these clouds are gray or white, and almost all the wavelengths are scattered equally. So in this case, we know visible light is almost white, right? Mostly white. So then we see some tinge of gray as well in the clouds, depending on the sizes of these droplets. When we have all these scattered waves together interfering with one another, it forms what's called a speckle pattern. So this is inherent in any wave-based imaging modalities. For instance, when you have a laser pointer and you shine it onto a rough surface, you will see this granular pattern, similar to what this image looks like down here of a laser speckle. So same thing happens in ultrasound. An ultrasound speckle also looks like this on the left. So it's caused by destructive interference of the sound between the scattered signals from these very small scatterers, on the order of sub-wavelengths. And as mentioned earlier, this can contribute to background texture of the ultrasound image. And the features of this texture also depends on the amount of scatterers that are in that tissue region that you're imaging. So the scatterer density also depends on the size of the scatterer, as well as any acoustic impedance changes within those scattering interfaces. Let's talk about fully developed speckle. So when the number of scatterers exceeds a critical value, number of scatterers inside the resolution cell, then the speckle pattern will turn into what's called a fully developed speckle. In this case, the amplitude of this tissue scatter will follow a Rayleigh probability density function. And this density function looks like this on the right. So we can also quantify this density function using a signal-to-noise ratio. Basically looking into the speckle signal-to-noise ratio, which is a function of the mean of the amplitude within that area, region of interest, divided by the standard deviation of that amplitude within the same region of interest. And for a fully developed speckle that follows a Rayleigh probability density function, this SNR value would be 1.91. So some speckle features also depend on the ultrasound frequency beam properties. and not on the macroscopic tissue anatomy. And also, depending on the SNR, the organization of the tissue structures can affect what the SNR is. So we'll talk about later how different types of these speckle statistics. So speckle can sometimes be characterized as noise, but in ultrasound imaging, speckle is deterministic and not random like in electronic noise. Speckle can affect image quality, such as the contrast and resolution of the image, which we'll discuss more in a subsequent lecture. But it can also be useful in some cases, such as when you're doing motion tracking, when you're doing Doppler imaging and tracking the motion of certain structures in the tissue. Also in elastography, when you're inducing some shear waves that will then be used to track the motion of the tissue, and then getting some elastic property or mechanical property of the tissue. Now in the lower left-hand corner here, you see an image of an ultrasound of a kidney, and you can see that most of the image has speckle in them. And this speckle is important for assessing the background texture of the tissue. So in summary, we've talked about what's scattering phenomenon. We looked at different scattering regimes, as well as specular scattering, Rayleigh scattering, and May scattering, which depend on the size of the object or the structure in the tissue relative to the ultrasound wavelength. We also looked into speckle and ultrasound images. Now this lecture will form the foundation for the next stages when we look at ultrasound imaging. Now let's change tracks slightly. In a previous lecture, we talked about the wave equation. Now let's derive the wave equation. So let's start out with several assumptions that we use to derive this equation. So if we have the exact description here, we first assume that the medium is lossless, meaning that there's no decrease in pressure amplitude with distance of propagation. So this will give us a nonlinear wave equation for lossless fluids. Nonlinear wave equation for lossless fluids. Another assumption would be if we assume that the amplitudes of the pressure variations, acoustic variations in the medium are negligible or very small, then we assume linear. And this will lead us to the linear wave equation for dissipative fluids. A linear wave equation for dissipative fluids. Now, if we assume both lossless and linear, assume lossless and linear, then we would get our linear lossless wave equation. Okay, and this governs wave propagation, what we have discussed in this course. Now, there are several acoustic variables to keep in mind, and some of which we have already discussed in other lectures. First, we have the particle displacement. Now, that's a vector. So, particle displacement, denoted by the notation epsilon. Then we have particle velocity. Again, that's also a vector, denoted by u. We have our equilibrium density, that's denoted by rho naught. Equilibrium density. And this is without the sound field. So sound field is off. And then we have our instantaneous density. And this is as the sound field propagates here through the material. We also define a condensation parameter, which is denoted by S. So this is condensation. And that is defined by rho minus rho naught divided by rho naught here. So the instantaneous density minus the equilibrium density divided by the equilibrium density. We also define equilibrium pressure. And this is without the sound field. So this is the pressure of the material at its resting state without the ultrasound field. Then we also define the instantaneous pressure, which is denoted by P. And that's the instantaneous pressure as the sound field propagates through the medium. Then we define the acoustic pressure, which we have looked into before, and that is denoted by the lowercase p. Acoustic pressure here, which equals the instantaneous pressure minus the equilibrium pressure. Okay? And then same as before, the speed of sound, longitudinal speed of sound, which is denoted by C, and our bulk modulus, which is a material property of the medium. And you will see that that is very much related to our speed of sound. Okay. In a previous lecture, we have looked into 3 equations which was used to derive the acoustic wave equation. So I'll just go over these 3 equations here. We talked about the equation of state, and that relates the pressure, acoustic pressure, to the density of the medium. We also have the equation of continuity. And that relates the particle velocity, u, to the density via the conservation of mass. And finally, we also talked about the equation of momentum. Which relates the pressure, P, to the particle velocity. And this is via the Newton's second law. So we will use these 3 equations. Now we're not going to derive exactly how these equations were derived, but we'll use this, put them together to derive the acoustic wave equation. So depending on several assumptions, we'll give an approximate version of each of these equations. So let's look at the equation of state first. So if we assume small amplitude variations in the medium, and this is after linearizing the exact description, then the equation of state becomes the pressure, acoustic pressure, equals the bulk modulus times the condensation term here. So P equals Bs. Next, the equation of continuity. Like here. Now this is assuming that the condensation S is small. So that is the density, instantaneous density, is approximately similar to the equilibrium density. And so the equation becomes rho naught partial derivative of s over dt plus this rho naught times the particle velocity equals 0. Okay. Now, finally, the equation of momentum. Now again, if we assume small amplitudes, then the equation of momentum becomes in this form. So rho naught partial derivative of du of dt equals minus this over p. Okay, so we'll use these three equations to help us derive the acoustic wave equation. Okay, now to derive the equation, what we do is we take the divergence of both sides in the equation of momentum. So let's write this down, equation of momentum. Then we would take divergence of both sides of the equation. So let's look back in the previous, right here. So our equation of momentum is right here. And we do the divergence of both sides. Okay. And this is what we would get. Divergence of rho naught partial derivative of the particle velocity over time equals negative this. So we'll call this relationship as our first equation. Okay. Next, let's take a look at the equation of continuity. Right here. What we are going to do is we're going to take the time derivative. Okay, time derivative of both sides in that equation of continuity. Okay, so let's look back at our equation of continuity here, right here. And we're going to do the time derivative of both sides. Okay, so what does that look like? We'll have rho naught partial derivative of the condensation over dt plus this. Now, denote that the density here is not dependent on time. So we don't do partial derivatives of this rho naught. That equals to 0. So again, this is a constant. So rho naught, we don't do a time derivative of this. Okay, so this is our second main equation that we'll use to derive the wave equation. Okay, now if we combine this first and second one, which we just derived, then we would get this equation, rho naught partial derivative of s, second partial derivative of s over t, and then this is our pressure term right here. Okay, so now the last step is to include the equation of state. All right, so with the equation of state, okay, we're given that the condensation equals the pressure divided by the bulk modulus. And note that the bulk modulus equals the density, equilibrium density, times the square root of the longitudinal sound speed here. So B equals rho naught c squared. Okay. So now we get this equation. If we plug in S into our equation here, right? So the final equation that we would get is rho naught divided by the bulk modulus times the second partial derivative of pressure, okay? And that equals our pressure term here, all right? So basically, from this equation, we just substituted the S so that we get pressure divided by the bulk modulus right here, okay? This is what we used. All right. Now in terms of the sound speed, okay, so we noticed that here rho and rho over B also equals C squared, right? So what we would get finally, okay, 1 over C times partial derivative of second partial derivative of pressure dt squared equals of P. So this is 1 over C. Okay, so our final linear lossless wave equation is this: d squared P divided by dt squared. All right, so this is our linear lossless wave equation. And it describes how acoustic pressure changes in space and time. Okay, see you in the next lecture. Thank you.